A very good evening to everyone. On behalf of India Space Lab, I warmly welcome all the participants to today's session of the Summer Internship and Training Program. We are honored once again to have Dr. Harishankar Sir with us today. As you already know, Sir is associated with IIRS ISRO and has extensive expertise in remote sensing, SAR interferometry, GIS applications, and disaster management studies. We look forward to another insightful and knowledgeable section under his guidance. With this, I respectfully invite Sir to take the session forward.
Okay, so good evening, everyone. Today's topic is related to the remote sensing. So, topic is seeing the unseen, the mysteries of synthetic aperture radar from space. So, you are already aware about the radar because radar has very long history of its development. So, radar can be used for many purposes. But here we will use the radar for the remote sensing purpose, and we will see what specific things can be captured by the radar devices when they are there in the space platform, or you can say they are with the satellite. Okay, seeing the unseen means we can see the things or the phenomena which are happening on the surface, which we cannot see directly from our eyes. Okay, but we can see through the radars. So what kind of the mysteries are there with the radar devices, especially when they are operated in the synthetic aperture mode? So what is the synthetic aperture mode? What is actually aperture? So aperture is, here you can simply understand, when the radars are operated, that time antenna is being used for the communication purpose, for the transmitting of the signals and the reception of the signals. Okay, so the antenna length actually is considered as a aperture, and if you want very high resolution information from the radar devices, then the real apertures cannot give very high resolution information, and this resolution can be enhanced if we are able to enhance the antenna dimension. Means if the longer antennas are there, then the resolution can be improved. So physically the size of the aperture or the size of the antenna, it's not possible to enlarge whatever is required for a desired resolution. Okay, so synthetically we are increasing the size of the antenna, so that longer antenna is basically called the synthetic aperture radar. Okay, so you can say synthetic aperture radar is nothing but the antenna length, or synthetic aperture is a antenna only, but the dimension of that antenna is increased synthetically. How we can increase that, I will discuss in the subsequent slides. Okay, so by means of synthetic process, we are increasing the aperture size, and then we are improving the observation space. Observation space means the resolution or the level of information on the earth surface, and that information we can utilize over certain phenomena which we cannot observe directly from our eyes. Okay, so so those things are basically, I have given the name like the mysteries of the synthetic aperture radar, when radar is there with the satellite in the space. Okay, so now coming first to the radar development. So radar stands for the radio detection and the ranging. So the name itself suggests that some radio signals are there which can be detected, and ranging means they can measure the distance. Suppose one signal is transmitted from the transmitting antenna, and the signal is propagating in a particular direction, and when this signal is interacting with any of the target, and then after interaction the signal is coming back. So by this particular information, means the received signal, you can detect whether some target is there, and if target is there, then how far it is from the transmitting antenna. So the distance between the antenna and the target can be calculated. That concept is called the ranging. And if you are able to find out the type of the targets, the characteristics of the target, that is called the detection. So these both the things, detection as well as the ranging, can be done with the help of electromagnetic signals which we are transmitting. And those signals may be in the microwave portion of the electromagnetic spectra, or maybe in the radio waves portion of the electromagnetic spectra. Okay, but initially the development was started in the radio waves, but later on the microwave portion was also utilized for the radar development. But if you see the starting of the development, historical perspective of the radar, so you can just think like a single nation has not done the development of the radar. So the development was started across the world, globe, and different countries had basically contributed in the development, and they developed the radars according to their requirements. Somebody is using for detecting the targets over the ocean, or over the, you can say, the water surfaces. Somebody is detecting the targets which are there in the air, or somebody is detecting the targets which are moving on the earth surface. So different people have different objectives, and accordingly they were involved in the development of the radars. But this development was started in the 20th century, somewhere in the 1900. So here you can see in 1904, a German engineer, Christian Holzmeier, invents a device called the telemobilescope for the traffic monitoring on the water with the poor visibility. Means some fog is there, or some aerosols are there, so the visibility is very poor, or some rain is there. So during that poor visibility situation, if some target is there, is coming over the water surface, over the ocean, then it was that time very difficult to know whether a special type of the traffic is coming or not, whether those are the enemy traffic of the enemies, or some other type of the traffic is there. So people have started, or German engineer has started monitoring such kind of the traffic using a device called the telemobilescope. And the concept of the telemobilescope was similar to the principle of the radar. So it was basically the first practical radar test to monitor the traffic over the ocean surface. Then in 1922, the American electrical engineer Albert S. Taylor and Leo C. Young of the Naval Research Laboratory, USA, locate a wooden ship for the first time. Means the wooden structures were also identified with the help of the radar devices. And this work was started in 1922 in America. Okay, and the first one was there in the Europe, in Germany. Then in 1930, Lawrence A. Heidland of the Naval Research Laboratory, USA, located an aircraft for the first time. Means this observation was done in the air platform. Then in 1931, these are few findings which I have taken from the literature. People have started the ship equipment with the radar devices. Antennas were used in the parabolic dishes with the horn radiators. And in 1940, different radar equipments were developed in the USA, Russia, Germany, France, and Japan. Basically, the in the developed world. So just after this 1940 Second World War is started. So the major objective of the radar development those days was how we can fight with the enemies, and we can track the movement of the enemies through the radar devices. Okay, So that the major use of radars was done in the at the time of the Second World War. So main focus was the military and the surveillance radar development, especially in the Second World War. And now, Sir Robert Watson Watt was considered as the inventor of the radar. But this is not the correct statement, because this is mentioned in the somewhere, because everybody is claiming we have developed first. Russians are saying we have developed first the radar. US persons are saying we have developed first, and German people are saying we have developed first. So there was basically a race, and people are claiming like that we have started the development of radar first than the others. But they were basically developing in their local scale, so the other people were not aware about. Okay, so in the literature, the Sir Watson Watt is considered as the inventor of the radar devices, and this is the picture of the Watson. Now, the objective is clear. We are not, because these devices or radar devices can be developed, can be used for many applications. Suppose you want to track some aircrafts, or you want to track some spacecraft, or the ship detection, or nowadays people are using it in the meteorology also. And some Doppler radars are there which are capturing the uh, atmospheric conditions, atmospheric parameters, and those information is useful for the weather forecasting and so on. And now in missile technology, people are using the radar devices. Now people are using the uh, lasers also for with the missile devices. But here we will use this radar for the remote sensing purpose. So you might be aware about the remote sensing, because if you coming to the basics of the remote sensing, so the name suggests the remote and the sensing. There are two terms only. Remote means this is not a TV remote. Okay, so remote means a distance, and the sensing means is a process done by a device called the sensor. Okay, so the sensor may be optical sensor, thermal sensor, infrared sensor, microwave sensor, radio wave sensors, and so on. So you can say remote sensing is a process to observe some objects from distance. Means the sensor which is used for the sensing purpose, that should not be in direct contact with the object under observation. So some gap should be there between the sensor and the object. If this gap is there, it means the process is called the remote sensing. It means sensing through distance. But in this remote sensing process, two other things are also involved. One is basically the energy which is moving between the sensor and the target. So sensor is means measurement is there, measurement energy is there, flow of energy is there, and the second one is the target. So now four things are there. You can say remote means some distance is there, sensing means some sensor is there, and then some object is there, and then some flow of energy is there. So four things are there. Means we are observing some object through some flow of energy from distance using some device called the sensor. So remote sensing is a process of observing some targets by means of observing the flow of energy through distance. Okay, means the distance should be there. You cannot say I'm putting my mobile phone near to me, and I'm taking the pictures. So this is the remote sensing. No, this is not remote sensing. Some distance should be there. If the device, suppose I'm putting some thermometer in my mouth and measuring the fever or the temperature of my body, it means the thermometer is in contact with my body, and we are observing something. Okay, it means this is not the remote sensing, because the sensor is in contact with the object. But if object is not in contact with the sensor, then you can say this is the remote sensing. For example, I'm right now looking towards the laptop, so I'm able to observe this laptop, but my eyes are like a sensor, and the laptop is a target, or you can say the object. So my eyes are observing the laptop, but eyes are not in directly contact, in physical contact with the laptop. So some distance is maintained, whether it is 10 centimeter or 20 centimeter or 1 meter. So some distance is there. It means this you can consider as a remote sensing. Means when I'm looking towards a device, or let us say laptop, so right now I'm doing the remote sensing. Okay, so you can say target is there, which is laptop here. Sensor is there, which are my eyes, and some distance is there between these two things. And the flow of energy is also there, because suppose this light is off, then I cannot observe, means some darkness will be there. I may not be able to observe the laptop. Okay, it means the flow of energy is there. The energy is coming from the tube light and incidenting on the laptop, and after incidenting this energy, the energy is reflecting, and that reflecting energy is moving towards my eyes, and my eyes are like the sensors, and they are observing the laptop. It means they're the complete example of the remote sensing. So target is there, sensor is there, distance is there, flow of energy is there. So nowadays people are saying, remote sensing as a science. Few people says remote sensing as a art. Few people says remote sensing is a technology. Few people says remote sensing is engineering. Okay, so whatever you want to say, you can say it, but this is a kind of process for of observations, because in science observation is must. Without observations you cannot do anything. So whenever you are doing science, it means you are observing. Okay, and how you are observing, that is important. Okay, and so many things are involved, like the distance. So the distance between the object and the sensors may be 1 meter, 2 meter, or hundreds of the meters, or few kilometers, or hundreds of the kilometers. Okay, if it is in few meters, it means the sensor is, let us say object is there on the surface, then sensor is also on the surface at few meters away from the object. So this may be a kind of remote sensing. If distance is, let us say, tens of kilometers, so you can say target is there, let us say aircraft is the target, and sensor is there on the surface, or sensor is there with the aircraft and observing the surface. So distance between these two things is tens of kilometers. This is also example of the remote sensing. So and another case may be like if you are putting sensor in the space, so the distance between the space, let us say satellite, and the earth surface is hundreds of the kilometers. But again, you are observing from the satellite, you are observing the earth surface. It means earth is a target, satellite having the sensor, distance between them is there hundreds of kilometers, and flow of energy is also there. So that flow of energy is important. Sometimes the flow energy is coming from sun. Sometimes sensor itself is generating some energy, and that energy is sent by the sensor towards the surface, and that energy after reflection again going back to the sensor and observed by the sensor. Okay. So my point here is, based on these things, you can classify the remote sensing. So as I mentioned here, the first classification you can do with the help of the electromagnetic spectra. Means which type of the energy you are using. Suppose I am able to observe my laptop, because my eyes are sensitive to the visible portion of the electromagnetic spectra. So you are already aware of electromagnetic spectra is ranging from the cosmic rays, gamma rays, X rays, ultraviolet rays, visible infrared, middle infrared, far infrared, microwave, and the radio waves. It means these are all level of energies. Means the sensor is working or capable to observe which types of the energy, whether radio waves or microwaves or thermal infrared or near infrared or visible or ultraviolet or X-rays or gamma rays or cosmic rays. It means this is the characteristics of the sensor. Means sensor is capable to observe which type of the energy. Okay, so the flow of energy is important. Means based of the energy itself, you can classify the remote sensing. So suppose you are using the visible portion of the electromagnetic spectra, then the remote sensing is called the visible remote sensing. If you are using the infrared energy, then you can say it is the infrared remote sensing. And if you are using the thermal infrared, then it is called the thermal remote sensing. And if you are using the microwave portion, microwaves, then it is called microwave remote sensing. And if you are using the radio waves, then radio wave remote sensing. If you are using ultraviolet, ultraviolet remote sensing. X-ray, X-ray remote sensing. Gamma rays, gamma ray remote sensing. Cosmic rays, cosmic rays remote sensing. But the ultimate goal here is, in case of the remote sensing, it means we are doing the remote sensing of the earth surface, and earth is covered by a very good envelope of the atmosphere. It's called the atmosphere. Okay, and atmosphere is having different layers: troposphere, stratosphere, mesosphere, thermosphere, and so on, ozonosphere, ionosphere, etc. So what is happening? The flow of energy, the natural source of energy is sun. So if the radiation is coming from sun, so, and let us say it is coming to the earth surface, but the most of the radiation is stopped by the atmosphere of the earth. It means whatever the radiation is stopped by the atmosphere, that radiation cannot reach to the earth surface, and earth surface is the target or the object. Okay, if a radiation is not able to reach on the earth surface, it means that radiation cannot be captured by the sensor, or you can say sensor is not capable to observe the earth surface in that particular wavelength which is stored by the atmosphere. Okay, so here I have mentioned only the optical remote sensing, infrared, thermal, and microwave. You can see the first one, the classification of the remote sensing based on the electromagnetic spectra. I have not mentioned cosmic rays, remote sensing, gamma rays, X-rays, ultraviolet rays, because these radiations are stopped by the atmosphere, and they are not able to travel across the atmosphere and not able to reach on the earth surface. It means these types of the remote sensing are not there. And same thing is happening with the radio waves. Radio waves are also not able to travel across the atmosphere. It means the radio wave remote sensing is also not there. So if you are talking about the remote sensing of the earth surface, so in that case, radio waves remote sensing is not there, ultraviolet remote sensing is not there, X-ray is not there, gamma rays, cosmic rays remote sensing are not there. But these portions of the electromagnetic spectrum, like visible, infrared, thermal infrared, and the microwaves, these radiations can travel across the atmosphere and hence can be used for the remote sensing purpose. And hence the remote sensing can be classified based on these types of the electromagnetic energies. So if visual portion is used, then visual remote sensing, infrared remote sensing, thermal remote sensing, and microwave remote sensing. So it is clear why the gamma ray remote sensing is not there, X-ray remote sensing is not there. But you see another analogous term of the remote sensing. That analogous term is called the astronomy. So astronomy is also similar to the remote sensing, because that is, in astronomy also we are observing the targets or the objects using these radiations. So if you talk about the astronomy, so as in astronomy, generally astronomy is applied for the other planets. If you are observing the other remote planets, that particular science is called the astronomy. But in those planets, atmosphere is not there. It means all the radiations can reach to the surface of those planets, and hence the astronomy can be classified as like cosmic ray astronomy, gamma ray astronomy, X-ray astronomy, ultraviolet astronomy, visual astronomy, infrared astronomy, thermal astronomy, microwave astronomy, radio astronomy. So you can say in astronomy all the wavelengths can be used, but in case of remote sensing of the earth, only these four types of the wavelengths can be used, and hence the classification of remote sensing is only four, while the classification of the astronomy is in all the wavelengths. Okay, so based on the energy which we are using, based on that we can classify the remote sensing like these four categories. And another one is the based on the source of energy, means the energy which we are using for the remote sensing purpose, it is coming from where? If it is coming from the natural source, which is sun, if it is coming from sun, it means it is coming free of cost, then it is called the passive remote sensing. And suppose in case of the sensor itself is generating this energy, and using for the remote sensing purpose, that type of the remote sensing is called the active remote sensing. The best example is, suppose I'm taking picture from my mobile phone in daytime. That time flash is off. Okay, and what is happening, whatever the natural light is there, using that light I can take the pictures. So that is the example of the passive remote sensing. And in the night time, my flash is on, mobile flash is on, and by making this flash on, it means the radiation or the energy is starting from the flash camera and incidenting on the target, and that reflected energy is captured by the mobile phone. So in that case, what is happening, the energy is generated by the mobile phone and used for taking the pictures, and that kind of function is called the active remote sensing. So it is very simple. If energy is coming from sun, then passive remote sensing. If sensor itself is generating energy, then it is called the active remote sensing. Okay. And another categorization is the last one, based on the platform. As I mentioned, based on the distance of the measurement, means that how much distance is there between the object and the sensor. If it is tens of meters, then it is called the ground-based remote sensing or the in-situ remote sensing. And if tens of kilometers distance is there between the object and the sensor, like if the sensor is there in the aircraft, then tens of kilometer gap is there or distance is there, then that kind of remote sensing is called the airborne remote sensing. If sensor is there in the space, then hundreds of kilometer gap is there or distance is there between the object and the target, target and the sensor, then it is called the space-borne remote sensing. So this is another classification. It means we can classify the remote sensing based on the distance also, means what is the level of distance, and based on the energy which we are using. Based on that we can classify, and we can classify from where this energy is coming, means source of energy we can classify. And the third one is the classification based on the number of bands. The number of bands is basically, see, when you're taking the pictures or the satellite images, so the image is in the form of the grid, and grid is nothing but a kind of the matrix. Okay, you might be aware about the determinants and the matrix. So satellite image is equivalent to a matrix. So sometimes what happens is one camera can capture only one matrix, it means only one band of the image. Sometimes what happens, the camera can capture multiple bands simultaneously or multiple matrices simultaneously. For example, one camera is operating over, let us say, in visible portion, suppose one band is captured from 4000 angstrom to 5000 angstrom, another one from 5 to 6000, another from 6 to 7000, another from 7 to 8000. It means a single camera is capable to acquire four bands at a time. And in the same way, few cameras are there which can capture, hundreds of the bands simultaneously, and few cameras can capture the thousands of the bands simultaneously. So depending upon these bands, the remote sensing can be classified as, if only one band they are able to capture, then it is called the panchromatic remote sensing. If tens of bands sensor is capturing, then it is called the multispectral. If hundreds of the bands are captured, then it is called the hyperspectral. If thousands of bands are captured by the sensor, then it is called the ultraspectral remote sensing. So I hope the classification of the remote sensing is clear to you. But this particular lecture is based on the microwave portion of the electromagnetic spectrum, because we want to use the radar devices. But in case of optical or thermal, some optical sensors are required. But in case of microwave, we can use the radar devices. Okay, so the microwave portion is lying between 1 millimeter to 1 meter of wavelength. So this long wavelength from 1 millimeter to 1 meter is further divided into sub bands. So those sub bands are mentioned here. Here you can see in the below table: K band, K band, KU band, X band, C band, S band, L band, and P band, according to the increasing order of the wavelength. So K band is having lower wavelength, K band is having more than K band, Ku is again wavelength is increasing, X band increasing. So gradually it is increasing. So P band is having the longer wavelength, or you can say close to 1 meter. L band is less than that. So ranges of the wavelengths and the frequencies are written in the subsequent column. So in radar devices, you might be aware about, like, radars are using the coherent signals. Coherent signals means they are working on a specialized radiations, not the ordinary radiation. Suppose the radiation is coming from this tube light, so this can be used for the radars. No, only single wavelength is useful for operating the radar, so that the signals can be coherent in nature, because the characteristics should not be fluctuating very fast, because these electromagnetic radiations are going in the sinusoidal waves. If multiple wavelengths you are using, so the resultant wave may be zigzag in nature. Okay, so in order to maintain the coherency between for the signal, then the signal should have monochromatic, or you can say single wavelength. Okay, and the signal should be polarized also, mean the direction of vibration of the electromagnetic field should be in a single direction. So you can say for the radar devices, we are using the coherent signals and we are using the polarized signals. So if you are coming to the polarization, so polarization may be elliptical polarization or the circular polarization or the plane polarization. Okay, but keep in mind, in the radar devices, we are using the polarized signal. Now coming to the why we use the microwave in remote sensing, there are number of advantages of the microwave remote sensing over optical or the thermal remote sensing. So the few I have mentioned here, like microwave signals are complex in nature, because the electromagnetic radiation have the electric field, magnetic field, and direction of propagation. Okay, but in case of remote sensing, magnetic field is not dominating, so the magnitude of the magnetic field is negligible. Only electric field is dominating, so we are analyzing only the electric field vector. So electric field vector, let us say E equal to E0 e to the power I theta. Generally we are writing the electric field vector in this form: e equal to e0 e to the power I theta. So e0 into e to the power I theta means it is a complex in nature, so we can write e0 cos theta plus iota times e0 sin theta. So it has real part plus imaginary part. It means the microwave signals are complex in nature, just like z equal to x plus iy. So real part plus imaginary part. So from this भैया रख दीजिए भाई. So this complex number is there, or you can say the microwave signals are complex in nature. It means from complex number we can drive the amplitude also. Let us say mod of z equal to square root of x square plus y square. This is amplitude of the signal, and we can calculate the phase of the signal also. Let us say phi equal to tan inverse y upon x. It means the microwave images or the images acquired from the radar devices are complex in nature. From those images, we can drive the amplitude images as well as we can drive the phase images. So phase images are very, very important. What the topic is seeing the unseen. So the phase images are very, very important, and those phase images can see whatever we cannot see from our eyes. So this particular lecture is now based on the beauty of the phase images. We will come to those things later. Another advantage is can give very high precision measurements, because here we are focusing on the phase images. So if you see the phase difference equal to 2 pi upon lambda into path difference, so lambda is of the order of the few centimeters. So path difference and the phase difference can be, because phase of the signal can vary from 0 to 2 pi only, or you can say from minus pi to plus pi. So the phase difference cannot go beyond this value. So maximum variation in phase of the signals can be 2 pi. So if you write, this 2 pi in that relationship, means phase difference equal to 2 pi upon lambda into path difference. So phase difference, suppose we are keeping as a 2 pi. So 2 pi equal to 2 pi upon lambda into path difference. So 2 pi is cancelled out by 2 pi. So path difference equal to lambda. So what does it mean? Path difference equal to lambda, and lambda is the wavelength. Wavelength of the microwave portion. Microwave portion wavelength is ranging from 1 millimeter to 1 meter. And if suppose we have developed, let us say, C bands are, see here, C bands are if we are using, so the wavelength is changing, ranging from 3.75 centimeter to 7.5 centimeter. This is the lambda. Okay, and suppose I am using a C bands are of 5 centimeter. So what will happen? The path difference will come of the order of 5 centimeter, because path difference equal to lambda. Lambda is 5 centimeter, so path difference equal to 5 centimeter. What is the path difference? Path difference means if any target on the surface has moved 5 centimeter, that can be measured from the phase difference of two signals, microwave signals. Okay. And then another important thing is this 5 centimeter displacement of target on the surface is happening in how much time? It is happening in 5 minutes, it is happening in 1 day, or it is happening in 1 week, or 1 month, or 1 year. Okay. If it is happening in 1 year, then that can also be measured from this phase difference. It means if any target on the earth surface is moving 5 centimeter in 1 year, that can be monitored from the phase images of the radar signals. And here I have taken the example of the C band. If you are using the X band, then the wavelength is here you can see 3.75 centimeter to 2.5 centimeter. So suppose I'm using the X bands are, let us say 2.5 centimeter. It means that path difference will come as a 2.5 centimeter. It means if any target is moving few centimeters, that can be easily monitored with the help of the radar signals. And that centimeter order movement can happen in 1 year or 2 years, sometimes 3 years or 4 years. So suppose some target is moving 2 centimeter in 5 years, you cannot see from your eyes. But if you are combining two radar signals, you can find out that very easily. Means one image of the first year and another image of after the 5 years. So these two images you are combining and you are calculating the phase difference, means phase of the first signal and phase of the second signal, which was acquired after 5 years. So the phase of one is, let us say, phi 1, phase of second one is phi 2. So phi 2 minus phi 1 is phase difference. So if phase difference is coming, let us say, pi by 2. So the pi by 2 equal to 2 pi upon lambda into path difference. So that path difference will come, let us say, lambda by 10, lambda by 20, something like that. So lambda by 10, lambda by 20, it will come of the scale of millimeter. It means if something has moved over the S surface from its original position to another position by few millimeter in 1 year or 2 year or 3 years, that can also be measured with the help of the phase images of the radar signals. So those things we want to see in the subsequent slides. What kind of things are happening, or what kind of the phenomena are happening, which are where the movement is involved of the few centimeter scale or the millimeter scale. Those things we will see. Okay. Another important advantage of the microwave in remote sensing is the microwave remote sensing can be conducted in active mode as well as in the passive mode. The optical remote sensing generally is happening in passive mode. Passive mode means we are using the sun energy as a source, sun as a source of the energy. But that optical remote sensing cannot be conducted in active mode, means we cannot develop a device which can send the optical energy for the remote sensing purpose. But microwave sensors can generate the microwave radiation, and that radiation can be used for the remote sensing purpose. It means microwave remote sensing can be operated or conducted in the active mode also. And what will be the additional advantage of the active remote sensing? Because that advantage is basically the passive remote sensing you can do only in the daytime, because in the night time sun energy is not there. It means in the night time you cannot do the remote sensing from this space. But radar remote sensing or the micro remote sensing is active remote sensing, that you can do in the night time also, because you are not depending on the sun's energy. You are having your own source of energy with the satellite, It means that energy you can use for the remote sensing purpose anytime, in the daytime or night time, or even sometimes rain is happening, sometimes fog is there, clouds are there. In any situation, you can use the active remote sensing. I will show you, because this active signals, so microwave signals can penetrate very easily through the clouds or through the fog or through the rain very easily. It means the effect of rain or cloud or any other condition is minimal in case of microwave radiation, but it is very high in case of optical or the infrared radiation. Okay, so another advantage is this microwave remote sensing is not dependent on the sun illumination, because in case of the active microwave remote sensing, not dependent on the weather condition. Doesn't matter whether it is rainy situation, foggy situation, cloudy situation, smoky situation, dusty, anything. It means this is not affected by these phenomena. It means it is very very good thing. Suppose if you are handling the disaster situation in the country. See, in our countries, number of disasters are happening. You start from the southern part, let us say in the Barren Island, Andaman Nicobar Island, so group of islands. So in Barren Island, the volcanic eruptions are happening. Okay, so volcanic eruption is a kind of disaster. And then in the Indian Ocean, we have a number of cyclones phenomena, or sometimes tsunamis are also happening. Okay, and if you are coming along the coastal region, then the land subsidence is there. Land is going downward slowly, slowly. And then we are coming to the, let us say, central India. Some drought conditions are there. Somewhere heat waves are there. It means this is the type of the disasters. And if you coming, let us say, towards the northern part, then flood problems are there. Cloud bursts are there. Then if you are moving over the, the Himalayan region, then landslides are there. Land subsidence is there. Then land movements are there. Plate tectonic movements are there. Glacier meltings are there. You see, all are some problems, and all these problems are related to the movement. I will show you how these are important. Okay, and whenever these these cloud bursts are happening, or extreme events are happening, or let us say landslide is happening due to heavy rainfall. In all such situations, clouds are there in the atmosphere. It means in such situations, if you are capturing the optical remote sensing data sets, they are not useful, because the optical energy cannot penetrate the fog or the clouds. It means the signal cannot reach to the surface, and you cannot understand what kind of situation was there over a particular area in the country during that cloudy situation, or during rainy situation. It means in any kind of the disaster situation in the country, the optical remote sensing is not that much useful. But if you use the radar devices, because radar signals are not much affected by these phenomena, it means during disaster situations, radar remote sensing data sets can be used to understand the disaster situation. So that is another advantage. And also next advantage is minimally affected by the atmosphere, because atmospheric also is very dynamic media. So atmospheric composition of the particles, like the ozonosphere or the ionosphere. The in ionosphere, the ions density is changing very rapidly with respect to time, as well as in the spatial context. Means the ion concentration over Dehradun is different, ion concentration in the Bangalore is different. It means the spatial variations are there in the atmosphere. And if you talk about, let us say, different times over the same area, let us say over the Dehradun, in the morning time, ion concentration is different. In the noon time, ion concentration is different. It means the composition of the atmosphere is changing very, very rapidly. If this composition is changing, it means the density of the atmospheric layers are changing, or you can say the refractive index is changing. If the refractive index is changing, so that time if radiation is passing through the atmosphere, that time that those signals or the radiation will be affected by these types of the particles in the atmosphere. So the optical radiation is much more affected by these types of the particles. But if you send the microwave portion, then those are minimally affected by the atmospheric composition. Somewhere, turbulence are happening in the atmosphere. So during turbulence also, the optical energy cannot pass, but microwave energy can pass, because microwave energy is of longer wavelengths. So longer wavelength has much more penetration capability, so they can penetrate the layer of the atmospheric compositions. So those signals are not very highly affected by the atmospheric compositions. So this is another advantage of the microwaves over the other portions of the electromagnetic spectra used for the remote sensing purpose. Then next is passive micro remote sensing, generally applied from the space. Because in case of passive remote sensing means sun energy we are using, and from sun's energy, very small amount of microwaves are reaching to the earth surface. It means from the larger area, very small amount of energy is moving towards the sensor side. It means that small energy cannot be captured by the satellite very precisely. So the resolution of the images in case of passive remote sensing is very, very coarse. So what happens? The sensor, or the sensor, you should keep very large distance. You cannot say sensor is near to the earth surface and you are doing the passive micro remote sensing. No, sufficient radiation you will not get it. And even you cannot put into the aircraft or airborne platform. So because the sufficient area, you cannot give the sufficient intensity of the signal. But if the sensor is put it in the space with the satellite, then the satellite can see the larger area over the surface. So from the larger area, sufficient intensity of the signals can reach to the sensor in microwave portion when the energy is coming from sun. So in that sense, this point is mentioned here. Passive microwave remote sensing generally applied from the space, not from the airborne platform. And active microwave remote sensing can be performed from airborne as well as from the spaceborne platform, because active means the sensor has its own source of energy. So it doesn't matter you are sending these signals from the air platform or the space platform. So in both the cases, active remote sensing can be applied. Okay. So these are the advantages over the of the microwave remote sensing. If I'm saying the microwave remote sensing, it means another name you can give the radar remote sensing. Okay. So now frequently I will use the radar remote sensing, not the microwave remote sensing, because here whatever the radar we are using, they are operating in the microwave portion of the electromagnetic spectra. Now another important thing is the interaction of the microwave with different media. As I mentioned, the microwaves have not dependent on the weather conditions like rainy, foggy, cloudy, even the vegetations and so on. So here we want to understand, if microwave are interacting with different types of the media, then what is the effect over the microwave radiations. So here I want to explain like the interaction of the microwave with rain, interaction with cloud, with soil, with vegetation, and with the atmosphere. So this slide is based on the rain, interaction of the microwave with the rainy situation. So here you can see in this graph, this side is the wavelength and this side is the penetration transmission, or percentage of the transmission of the signal through the atmosphere. So here you can see this portion, shaded portion, is showing the effect of microwave due to rain. So the lower line means this line is showing the high intensity rain, and this is saying the low intensity rain. It means high intensity rain can affect the microwave, because here you can see here is the percentage. Percentage is around 15% if heavy intensity of the rain is there, and if low intensity rain is there, then around 60% radiation can transmit, or can transmit from the upper portion of the atmosphere towards the earth surface. And if see here, the transmission rate is very close to 100%, means all the radiations can transmit. But what is the effect? See here, If the wavelength is smaller, then the effect is dominating. The moment wavelength is increasing, let us say over this portion of the microwave portion, electromagnetic radiation, the transmission is very close to 100%, means no effect of rain. It means if you are using the wavelength, longer wavelength, then the longer wavelengths are not affected by the rain. But the shorter wavelengths are affected by the rain. But that effect is increasing if wavelength is decreasing. So you can see in X bands are, what is the wavelength? 2.5 centimeter to 3.75 centimeter. So you can say X bands are, or X band radiation or radars are much affected by the rain, especially during the heavy rainfall. Okay, but the effect of microwave on rainfall is very less if the wavelength is uh, going beyond 4 centimeter. Let us say 4 centimeter is somewhere here, so around 80% radiation is transmitting. So you can say if you are using the wavelength of more than 4 centimeter, then effect of the rain is negligible. So if you are using C bands are, or S bands are, L bands are, P bands are, so the effect of rain is negligible. Okay. Now this slide shows the effect of cloud on microwave. So the similar effect is you can observe here. So this side is wavelength, this side is the transmission rate, and here you can see two types of the clouds are there. One is called the water cloud, another one is called the ice cloud. So you see whatever the wavelength we are using, the for the from the ice cloud transmission rate is always 100%, or you can say any wavelength in the microwave portion is not affected by the cloud if the cloud is ice cloud. But if it is water cloud, then the smaller wavelengths are affecting, but the longer wavelengths are not affecting, because for the longer wavelength, the transmission is very close to 100%. So again, the longer wavelengths are not having effect of cloud. Doesn't matter what kind of the cloud is there. Okay. So by this way, you can understand. Another one is the soil. Soil, you can see this is the surface of the soil, which is very zigzag. And if it is a dry soil, means moisture content is very very less. So what is happening if radiation is coming from this side? So part of it is getting absorbed, and part of it is reflecting. So you can say partly it is reflecting. So when it is going back towards the satellite, so very small amount of energy is received by the sensor, and you can say the moderate level of intensity you can observe from the dry soil. But if the soil is wet, it means water content is there with the soil. So surface is there, but water content is also there. So what is happening? The absorption part is not there, or you can say the transmission is not taking place. Okay. So the entire energy is getting reflected, and the much more energy will reach to the sensor side. In that case, the high amount of reflected energy will receive by the sensor, or you can say high intensity signals can be captured by the radars. In that case, the more information of the soil can be captured. So here moderately less information, here more information. But another situation is also there, that is called the flooded soil, means the water is there on the above of the soil surface. So in that case, what is happening? The surface becomes, specular in nature. So water surface is very very smooth in nature. So what is happening? The signal is coming from the sensor side, and it's completely reflecting in another direction. Sensor is this side, but energy is going in another direction. So the backscatter energy is negligible, and the sensor is not able to capture any of the energy. It means in this radar images, if the flooded soil is there, then the black pixels you will observe. But if soil is wet, then the maximum energy you will receive. You can say the bright pixels will be there. And in case of dry soil, the intensity is of the moderate order. It means grayscale pixels you will observe. Okay, if these types of the soils are there on the earth surface. Now coming to the vegetation like the agricultural lands or the forest patches. So a different wavelengths interacts with the vegetation differently. Let us say this is the X band, 3 centimeter wavelength. So the wavelength is only interacting with the canopy of the trees. They are coming and going back from they are interacting with the canopy structure, leaves only, and then going back. It means the major energy is received by the sensor. And in case of C band, comparatively longer wavelength, here it is wavelength is 6 centimeter. So what is happening? The moment the wavelength is increasing, the penetration capability is increasing. So in this case, the signal is not only interacting with the canopy, it is also interacting with the branches of the trees. So the penetration is increasing. So this way the signal is penetrating. Okay, so here you can get the information from the canopy as well as the branches. But if you are increasing further the wavelength, let us say L band, which is let us say 24 centimeter, then the radiation is penetrating from the canopy, then going to the trunks, and a few signals are reaching on the earth surface also, and then going back towards the satellite. It means if longer wavelength you are using, then you can investigate the canopy structures, trunk structures of the trees, as well as the situation on the earth surface. Means what is the soil characteristics, what kind of the features are there over the earth surface, just in between or just below the trees. So that information you can capture, and this is the beauty of the longer wavelength. If you are further increasing the wavelength, then what is happening, the signals are penetrating, multiple signals are reaching to the earth surface, multiple signals are back scattered from the trunk as well as from the canopy. It means a large amount of information you can collect from the vegetation if longer wavelengths are being used. Here, what kind of information you are getting here in case of X band? Only the information of the canopy. Here, the information of the canopy plus branches. Here, the information of the canopy trunk as well as the small information of the soil. Here, huge information, canopy, branches, trunks plus soil, entire information you can investigate very easily. And the biomass means the total volume of the tree can also be investigated by the longer wavelengths. So P-band radar devices nowadays people are frequently using for estimating the biomass of the forest patches, means how much bio content is there for each tree. So the moment wavelength is increasing, the penetration, because of the longer penetration capabilities, the more information can be gathered using these remote sensing products. Now another thing is the atmosphere. So in atmosphere there are two major layers or spheres. One is called the troposphere, another one is called the ionosphere. In the ionosphere, ions are there. In the troposphere, molecules are there, of molecules of the different types, whether it is fog or the water droplets, etc. So the signals are disturbed in either in the ionosphere or in the troposphere. So that signal delay, can be estimated with the help of these relationship. So these relationship I'm not explaining right now, because thermodynamic variables are involved here, like the temperature is there, pressure is there, and partial vapor pressure E is there. So if you're, and then all of them are affecting the refractivity, or you can say the refractive index. So more refractive index means more density of the media and more delay is there. So here you can see the delay in the troposphere is the function integration of the refractivity, and refractivity is depending upon these three parameters, and some constant coefficients are also there. And same way in case of the ionosphere, the total electron content, TEC, total electron content is measured, and based on that electron density, the total delay in the ionosphere can be estimated for the microwave portions of the electromagnetic spectrum. Now coming to the microwave remote sensing systems. So these are again of two types we have already discussed: passive microwave remote sensing, active microwave remote sensing. In case of passive remote sensing, sun energy is used, but the major devices are called the radiometers. And those radiometers can be operated in the real aperture mode, means using the actual length of the antenna, or these radiometers can be operated using the synthetic aperture also, means enhancing the aperture size synthetically, and in that mode also the radiometers can be used. Okay, and these are passive devices. Some sounders are also there just to investigate the atmospheric conditions using the microwave portion. In case of active microwave systems, these are the radars, and radars may be, imaging radars and the non-imaging radars. Examples of the non-imaging radars are the altimeters and the scatterometers. So they are not directly taking the pictures; they are, uh, um, observing only the attribute information over the Earth's surface. Scatterometer, the scattering coefficients are scattering properties are measured. Altimeters, height variations are measured, and in the imaging radars, sorry, in imaging radars, images are captured, and those images can be captured in the actual aperture, with actual aperture, or with the actual antenna, or with synthetic antenna or synthetic aperture radar. So here the synthetic aperture radar, in short, we call it the SAR, and here it is called a real aperture radar means RAR. So now I will frequently use the term synthetic aperture radar. Okay, in case of interferometry, the synthetic aperture radar is useful. So now frequently I will use the term SAR. So when I say the SAR, it means it is a imaging radar and working in the active mode. Now coming to the radar devices. So radar devices are the side looking, because generally in the optical sensors or thermal sensors, they are nadir looking, means from the orbit they are directly looking towards the earth surface and capturing the images. But radars are not doing this way, means radars are not capturing the images in this particular direction. You can see the radar is not directly looking towards the earth surface, means this is not looking towards this side, this is looking towards this side. So this is called the side looking. So it may be, left looking or the right looking. Suppose satellite is moving in this direction, so if it is left side it is capturing, then it is called the left looking radar. If it is capturing the images through by looking in the right direction, then it is called the right looking radars. Okay, there are advantages because the ranging capabilities we want to utilize here. So what is, how it is basically working, that concept I want to mention here. Radars may be, the continuous wave radars or the pulse radar. So in remote sensing case, we are using the pulse radar. So what is the pulse? Pulse is basically a bunch of signal which is transmitted from the sensor only for a very small interval of time. For example, one bunch of signal is transmitting from the radar. Let us say this bunch. So this bunch is, let us say from here it is starting, and the end of this signal is here. So for a very small time, the signal was propagating. So that bunch is called the pulse. And how long it was transmitted? Let us say 1 microseconds, 1 millisecond, something like that. So that time is called the pulse length. So here you can see the total length of this signal in terms of time is called the pulse length. Okay, so multiple pulses are transmitted from the sensor after certain intervals. Let us say one pulse was transmitted, then 1 millisecond gap is there, then another pulse is transmitted, then again 1 millisecond or nanosecond gap is there, then another pulse is transmitted. So that way a sequence of pulses is being transmitted from the transmitting antenna, and they are propagating like, this way, just like a wave front. So they are moving this way, and see, when it is reaching to the earth surface, then over the earth surface different types of the targets are there. So here I have mentioned only two targets. So here you see, here when the signal is traveling like this, then if signal is coming over this side, then what is happening, this portion of the signal is interacting with the target, but the another portion means that this portion is not interacting with the target. So that portion will move ahead, but whatever the portion is interacting with this target, that will start going back. So you can see here, whatever the portion is interacting with this target had started going back like this, again in the form of the pulse. Okay, and the another remaining portion is moving ahead, no target is there in between, but if it is reaching at this location, then another target is coming, After interacting with another target, the signal will go back. So now see, from the same pulse, one portion is starting going back first from here, and another portion is starting going back later on. So see, and these are called the backscatter signals. When the signals are going back, means these are the backscatter signals, or you can say the backscatter pulses. But here now we will call it the backscatter echo. So what will happen? This particular signal or this particular echo will reach to the sensor first, and this pulse or this echo will reach to the sensor later. Means with respect to time, these echoes are differentiated. So the sensor can understand the first echo completely, and then later on the another echo is coming, the sensor can understand the another echo also. It means the sensor can easily identify, okay, some object or the target is here and some target is here, just because of these different echoes, means echoes which are reaching to the sensor at different times. And just opposite, you can think, if suppose the echoes from all the targets are reaching to the sensor at the same time, that time the sensor cannot differentiate this target, because all the echoes are reaching simultaneously. It means sensor is not able to understand this a portion of the echo is coming from where. Just like if you are sitting in a room and you are speaking loudly, and then some echo is coming from all the walls of the room, and you are in the center, it means the echo will come from all the walls simultaneously. So that time you will not be able to understand from where, means a particular echo is coming from which wall first. It means you cannot differentiate the walls with the help of the echoes. Okay, but since this sensor is side looking, so obviously the targets are there on the surface, they are at the different distances from the sensor. If they are at the different distances, it means whatever the backscatter echo is there, that is automatically differentiated because of the distance. It means whatever the echo will go back, that will be separated by some time with each other, and hence the sensor can capture those echoes very easily. It means this is the beauty of the SAR sensor. And suppose if all echoes are reaching at the same time, the sensor is not able to capture. And you see, just imagine, suppose the sensor is looking another side, that directly toward this side. If one target is here, another target is there, so from both the targets, the backscatter echo will be reaching to the satellite at the same time. If they are reaching to the satellite at the same time, it means the sensor is not able to differentiate. That's what the radar devices are not operated in the neither looking, they are operated in the side looking mode, so that according to the distance they can easily understand the response of each and every target very easily. Okay, so this is the fashion. And this range means this particular focus means whatever the area it is covering, so this is called the swath. And this range from here to here, this is called the slant range. So this is near to the, because if we draw perpendicular over here, so this line, this particular line is close to that perpendicular line, so this is called the near slant range. And this line is far, so it is called the far slant range. And if you want, you can draw a line in between also, that is called the central slant range, or sometimes we call it the Doppler range. Okay, so the Doppler concept I will explain sometimes later. So you can see this is called the near slant range, this is far slant range, this is called the swath. Okay, and this gap, this angular difference, this is called the beam width. So if this beam width may be smaller or the longer also. So if you want to capture the high resolution images, the beam width should be as small as possible, so that you can easily identify or you can capture the high resolution images. Okay, and coming to the this slant range resolution, you see this particular pulse is going, and if it is reaching here, then the front portion of this pulse is interacting first, and that is coming back. Okay, so when it is traveling half distance, so that time the back portion will also coincide. Okay, so the half of the pulse length is governed by the slant range resolution. Okay, so here you can see the slant range resolution is slightly less than tau by 2. Tau is the pulse length, or in general you can say that approximately equal to the c tau by 2. C is the see tau by 2, tau is the time only, so time tau by 2 is also time. So but if you are talking about the resolution means it is a dimension, a spatial dimension. A spatial dimension means a distance is there. So how you can convert this time into distance? If you are multiplying this with the speed of light or speed of the signal, and the speed of the signal is the c. So if you're writing c tau by 2, so c tau by 2 will be the slant range resolution. Okay, so this is the working principle of the radar in case of the microwave, in case of the remote sensing. Now see this particular way. See, this is very interesting how it is basically capturing. So satellite is continuously moving, so that is called the track or trajectory. Now see, what is this? See, uh, let us say this side, the satellite is moving toward this side. So this is the actual antenna length of the satellite. So satellite is continuously moving. Let us say sometimes the antenna is here, sometimes antenna is here, sometimes antenna is here, and so on. But you can observe when the antenna is here, so that time the antenna is capturing the data from here to here. You can see the coverage of this. Okay, so from here to here the data can be captured by the real aperture when a satellite is at this position. And now just concentrate over this particular target, which is by the red color. When this satellite has reached here, that time the coverage is from here to here. Okay, it means that this target is still visible in the satellite image. And when the satellite is here, that time again the coverage is from here to here. Then again this target is visible in the image. And when the satellite is here, then again the target is visible, red target. And when the satellite is here, that time again the red target is visible. When the satellite is here, then again the red target is visible. But if the target is satellite is here, then in this coverage the target is out. So what is happening when the satellite is moving from this position to this position? So in during entire journey from here to here, the this particular target is in contact with the satellite. It means this particular length from here to here can be considered as a another antenna length, but this is not the physical length, or this is not the real aperture. Evans. So this is not the real aperture, but the distance from here to here, it is acting like a antenna only, because from here to here in the entire journey, this is particular target is in contact with this particular sensor. It means the distance from here to here is called the synthetic aperture, and the length antenna is called the synthesized antenna. So the synthetic antenna is much more longer than the actual antenna. So you can say the antenna length is increased, so the resolution capabilities of the sensor has increased. दिवांश दिवांश आवाज मत करो, आप अंदर चले जाइए. Okay, so so what is happening? This you can understand by another way also. Suppose I'm looking the screen of the this laptop from here, then I can only observe the intensity in this view. And suppose I'm looking the screen from this side, as well as from this side and this side. It means my observation angle is, let us say, somewhere 60 degree or 70 degree.
it means my observations will be better and better. And suppose I'm observing a particular target from 360 degree, I can observe more information about the target. So the same way you can compare. If the antenna is only here, that time a small amount of energy is observed about this particular target. If from here to here continuously the satellite is observing this target, it means more and more information it is capturing about this target. It means more information about this target means the resolution of the images can be improved. So that way, by means of increasing the antenna length, the resolution is improved. So this is another way of improving. Now coming to the radar images, suppose radar images are captured, then what is the quality of those images? Means what are the pixel values in the images? So दिवांश नहीं मानोगे, बोलना नहीं है, आप उधर जाओ, जस्ट मिनट, सॉरी दिवांश बोला नहीं, बोलना नहीं, उधर जाओ. So now if you want to understand the images, see, the visual interpretation of the optical images is very simple. You can see on the Google map, so all the features are very, very clearly visible. Then you can understand there is the road, there is water body, there is forest, or there is building, and so on. Very easily you can understand. But if I'm giving you, the radar images, then it becomes very difficult to understand or to tell what kind of the feature is where. Okay, so you can say the interpretation of the radar images is not that much simple as in case of the optical images. So to interpret the radar images, some extra skills are required, and those skills you can improve if you understand the effect of different parameters over the radar images. So here I have classified those parameters into two categories. One is called the system parameters or the system properties. System means sensor parameters. System means sensor. So you can say if you are changing different sensor parameters, then the quality of the images is changing. Or you can say the pixel values in the images are changing if sensor parameters are changing. Another set of parameters is the terrain parameters. Terrain parameters mean target parameters, means or feature parameters. Terrain over the Earth surface, different types of features are there. So their feature characteristics may be different. It means their responses in the radar images will be different. So how they are getting changed? So those we will try to understand. So in case of system parameters, you can understand like the frequency or the wavelength. If we are using different wavelengths, the quality will be different. If we are using different polarization, as I mentioned, elliptical polarization, circular polarization, or the plane polarization. Plane polarization may be horizontal polarization or the vertical polarization. So which polarization you are using, and hence the response in the images will be different. And then a speckle effect, that is kind of the noise introduced in the images by means of interference of the signals within the pixels. So some disadvantage or noise is involved, and that kind of things you can understand. Beam geometry. Beam geometry means, as you know, the radars are side looking devices. So this particular angle is called the look angle. In this side look angle is 0. If this tilt is like this, it means look angle is there, or you can say the depression angle is there. So if depression angle is large or small, so you can say the beam geometry is changing, means this side it is looking, or this side is looking, or this side is looking like this, means how much tilt is there. So based on that, you can identify or the effect in the image quality. And then of course the spatial resolution means how synthetic aperture you are using, how long the synthetic aperture you are using, and accordingly the spatial resolutions are changing. Okay, and these radar images are governed by two types of the resolution. One I've already explained, the slant range resolution, and another one is called the azimuth resolution, means the resolution along the trajectory of the satellite. So satellite is moving, let us say, in this direction. So along the track of the satellite, the pixel size is governed by the azimuth resolution. And another set terrain parameters are of different types, like surface geometry. Surface geometry, like it is a plane area or it is a undulating area. like the hilly terrain, then the response will be different. Dielectric property, just like some metallic structures are there on the surface, or the vegetation is there, or let us say dry soil is there, or the wet soil is there. So wet soil is having more electrical dielectric properties. Okay, so accordingly the response in the images will be varying. Surface roughness, roughness means how much zigzag the surface is there, plowing is there, or the smooth surface is there, rough surface is there, something like that. So rough surfaces gives more response, and smooth surfaces are giving less response. It's like the water surface, which is rough, which is basically smooth. So smooth surface is giving less response, but rough surface is giving more response. And same way the volume scattering, as I have shown you the scattering from the vegetation, where the canopy structure is there, so multiple bounces are happening. So that multiple bounces are called the volume scattering. So volume scattering is happening, it means more response you will get. In case of surface scattering or dihedral scattering, less response you will get. Okay, so these parameters I will go quickly, then I will come to the application part. So here you can see the effect of the wavelength of the frequency. So here you can see this is the sentinel image. These upper two images are sentinel images, and lower two images are the Allos pulsar two images. Allos pulsar is the L band SAR, and sentinel one is the C band SAR. So this image is the BH polarization. BH polarization means generally we are writing a polarization with dual letters. So first letter V stands for vertical, means vertical, and H stands for the horizontal. So the meaning of this one is the when the signal was transmitted from the satellite, so that time the polarization of the signal was vertical plane polarization, and after interaction the signal went back to the satellite, and that time satellite has captured or received the signal. So the at the time of reception of the signal, the polarization was horizontal, or you can say a sensor transmit the signal in vertical polarization and receive the signal in the horizontal polarization. So you can say vertically transmitted, horizontal received. So this polarization is there, and wavelength is C band, and you can see the same polarization, BH polarization, but in case of L band. So you can observe the difference between this image and this image. Here the dark area is gray, this one is gray, this one is dark. It means over this area less response you are getting, just because of the wavelength, change in wavelength. Same way here, this is BB polarization, and this is BB polarization of the L band. So the responses are very clearly visible here. If you are observing the images in one polarization, one wavelength, and the another wavelength in the same polarization. Now coming to the speckle, as I mentioned, this is because of the interference, some noise is involved, and this is because of the constructive and the destructive interference. Somewhere the at the location of the constructive interference, the intensity of that pixel is increasing beyond the actual energy, and in case of destructive interference, the energy is reduced from the actual energy, just because of this interference. If the two signals are superimposing with each other, so that time the intensity is either decreasing or increasing from the actual value. So what you can observe in the image, these types of the grainy structures you will observe, and these types of the behavior tells you the speckle effect is there, or speckle noise is there in the image. And this is the viewing geometry, like this I want to tell you, this is a sensor. So this side, if it is looking, so this angle is called the look angle, and this angle from the horizontal line is called the depression angle. And if this is the target, so the angle between this line and the vertical is called the incidence angle, and this angle from the horizontal is called the grazing angle. And if undulating terrain is there, then the incidence angle is called the local incidence angle, because here you cannot if you draw a perpendicular, so perpendicular will be towards this side. So this particular angle between the perpendicular and the incident light is called the incidence angle, but this is the local incidence angle. But this local incidence angle, if you add this slope angle in the local incidence angle, then you will get the actual incidence angle, which is from this vertical. Okay, So here you can see the image is acquired in different incidence angles. See here, this image acquired at incidence angle with 58°. This is 45°. This is 28°. So the image quality is different at different incidence angles. Now this is coming to the resolution, range resolution. As I already mentioned, the slant range resolution is c tau by 2, which I have already explained. And this slant resolution means resolution along this particular line. If we project this resolution over the ground, then it is called the ground range resolution. And this ground range resolution expression will be c tau by 2 divided by sine of theta, and theta is the look angle, this one. Okay, and if you're writing in terms of gamma, which is diffraction angle, so theta equal to 90 minus gamma. So in place of theta you can write 90 minus gamma, then it will be cos gamma. So you can write expression c tau by 2 cos gamma. Okay, so now from this particular table you can understand I'm putting different values of gamma or different values of theta. So here let us say theta is 10°, 30°, 50°, 70°. Then slant range resolution I'm calculating from this expression only, and everywhere I'm getting same value. It means the resolution, slant range resolution is not changing if you are changing the incidence angle. It means for every incidence angle or whatever the look is there of the satellite, everywhere you will get the same slant range resolution. But when you are projecting over the ground, that is called the ground range resolution. If you are calculating the ground range resolution, that is depending upon the look angle or the depression angle. That time if you are calculating, then you can observe this ground range resolution numerical values are going to decrease. It means the resolution is increasing. So you can say the moment you are increasing the look angle, the ground range resolution is improving. It means here you can see in case of this near slant range, the theta is small, and in case of far range, the theta is more. If theta is more, it means let us say 70°, and in the near range, theta is small, let us say 10°. So at in near to the near range, the pixel size is 29 meter, but in far range, the pixel size is 10 meter. It means at far range, the spatial resolution is better. In near range, the spatial resolution is coarse. It means, see, generally when we see, suppose you are sitting here and if you are observing, then here these things you can see very clearly, but here the things may be some noise will be there or you cannot see very clearly. But in case of radar, it is just opposite. The things which are close to the far range are clearly visible by the radar, but the things which are close to the near range is not clearly visible to the radar. So this is an additional advantage. If you want to see very far, it means you can see things very clearly. As the theta is increasing, the resolution is improving. So you can say if you are moving from near range to far range, the spatial resolution, ground range resolution is improving. Okay, and here you can see this range resolution, slant range resolution is c tau by 2. C is the speed of light, tau is the pulse length, which is not going to change. Hence, the slant range resolution is uniform throughout, and it is also not depending upon the height of the sensor. Means where we are putting this sensor, whether in the air platform or in the space platform, or let us say if I'm putting this radar at moon, it doesn't matter. Means slant range resolution will remain the same. So irrespective of satellite position, the resolution remains constant. It is good thing actually. Suppose I'm putting this sensor in the Mars, and from Mars you can observe the surface very easily. Okay. Anyway, okay, let's go ahead. So now another resolution is called the spatial resolution in the direction of azimuth. Suppose satellite is moving in this direction. So this is the azimuth direction. So the resolution along this direction is called the azimuth resolution. So azimuth resolution can be calculated like slant range into beta. Beta is the beam width. So beam width can be written as lambda by L. L is the antenna length. So slant range, here you can see from these three parameters. Slant range. So if you talk about the near range and the far range, so near range is less, far range is larger. So in case of near range, this value is small. It means is azimuth resolution. If you are calculating for a given value of lambda and given value of L in near range, the numerical calculation, numerical value will be less. It means the pixel size is small. It means resolution is good. And if you calculating this azimuth resolution at far range, so far range means slant range is more. At far range, it means the numerically this value is large. It means pixel size is large. It means at far range the azimuth resolution is coarse. So now you see in near range azimuth resolution better. At far range azimuth resolution is coarse. But in case of ground range resolution, at near range ground range resolution is coarse. At far range ground range resolution is better. Means just opposite of each other. Means ground range resolution and azimuth resolutions are just opposite to each other with respect to the near range and far range. So there is a competition actually. Okay. So we have to decide in such a way that the sufficient pixel size we are able to get. So according to the slant variation in slant range, you can identify this azimuth resolution is changing from which direction to which direction. And again, according to the lambda, you can say, suppose lambda is smaller in case of X band. It means X band images can have better azimuth resolution. P band images will have the coarser azimuth resolution. And same thing you can classify based on the value of L. L means antenna length. Means L is small, then overall you will get the more or high numerical value. It means smaller antenna will give you the coarser resolution, coarser azimuth resolution. If L is large, then numerically the overall you will get less number. It means longer antenna or the synthesized apertures will give you better azimuth resolution. Okay, so from these expressions you can understand. So the 2-3 points I have mentioned here, you can read later. Now dielectric properties, just like involvement of the water, it means dielectricity is increasing, so you can visualize those pixels, as a brighter pixels in the image. So wherever the brighter things you are observing, it means the dielectric properties are high over those locations. Okay, if some metallic things are there, those will also be highlighted by a bright pixels. So wherever the electric properties are high, brighter pixels you can observe in the images. Here you can see the track, railway track. The railway track, the dimension is very small, but it is very clearly visible in the radar images. But this thing you cannot observe in the optical images. Okay. Now surface roughness. Surface roughness is another parameter. Like this surface is rough, so diffuse reflection will happen, and more amount of energy you can observe. In case of specular reflection, no energy will observe because this energy is going in another direction. If corner reflectors are there, suppose energy is coming here, then incidenting towards the another building side, then from there it is reflecting and moving towards the sensor. It means this is called the dihedral reflection, so more energy you will get. So this type, if the more surface roughness, more response. Less surface roughness or smoothness in the surface, and less response. You can just understand. Okay. Now you can compare here the SAR image versus the optical image. The upper one is the optical image. Here see some fog or the cloud is there. You cannot able to see the earth surface in the optical images. But this is the SAR image. It means the structure over the earth surface you can understand very easily. So here I have mentioned the SAR sensors are sensitive to earth surface structures and the moisture content. Wherever moisture is high, brighter pixels you will observe. Wherever the very good structures are there, metallic structures or any other type of the structures, you will get the response. So my point here is, if any disturbance is there in the atmosphere or near the surface, that time optical images fails. But SAR images can give you the exact information. Here you can see another example. Suppose this is the optical image, this is the SAR image. Here you see some forest patches are there. But in case of SAR images, forest patches are giving very good response. Okay. Same way here, these things are giving very good response. Here some structures are there, and these structures are very clearly visible in this R image. Here you can see some transmission line is there, that is also visible. And see here, this structure, this one is not visible in the optical, but it is visible in the SAR image. So these smaller structures which are having very good dielectric properties can be easily visible in the radar images, but not visible in the SAR images. Suppose some transmission line is going from here, you cannot observe in the optical images, but you can clearly see in the radar images. Okay. And same thing here, this is the optical image and this is the radar image. Here in optical image you are able to see this one kind of polygon, but in case of radar images the internal structures you are able to identify is what kind of the structures or geometries are there in the over that surface. This is another example of the radar images. See here, these structures, radar images, the bridges you can easily identify the structures of the bridges. But if you are taking the pictures of the optical images, that is taken in the another view, so the entire structure is not clearly visible in the optical images. Now using the radar images, multiple outputs can be generated, like 3D mapping, digital elevation models can be generated, tomography can be generated, the different portions of the buildings and which portion is reflecting more energy and emission kind of things. Those things you can easily identify with the help of the radar images. And differential interferometry, beautiful fringes you can observe, and what kind of deformation is happening, the deformation rate you can observe. And differential interferometry, some subsidence is happening, means land is going downward, so those things you can clearly analyze with the help of the SAR images. So here you can see this portion is going to subside, so the subsidence patch is very clearly visible in the radar derived outputs. Here you can see this is the oil spill in the ocean. In ocean, most of the places, the zigzag response is there, but wherever the oil is there, so that oil spill is very clearly visible in the optical, sorry, in the SAR images. But this you cannot observe in the optical images. Same thing here, the roughness maps, wherever the roughness is there, more roughness, rough surfaces are there, clear, bright pixels you are observing. Here you can see the agricultural patches, different types of the scattering you can classify, and you can classify all these fields very easily. So small fields you can very easily visualize in the radar images. Here the flood situations are shown. So these are the some beauties of the SAR images. Now what is happening actually in the radar images? Here you can just keep some patience and try to understand. In the starting I mentioned the SAR signals are complex in nature. So z equal to x plus I by means real part plus imaginary part. Then I told you I can drive the amplitude like mod of
Attention all the participants. I guess there is some network issue with sir. He'll be right back. By then, kindly maintain discipline. All the participants who have a query regarding the 45-day training and internship, your sessions, that the sessions you all are attending, which you are getting trained, those will be held only till 18th of May. After 18th of May, your project work will start. Means the project that you have to build for your internship, that will start. So the sessions are only till 18th of May. After that, the rest of the time is for your project.
Yeah, sorry, actually, some internet problem was there. Now it is okay. Let me start disable. Okay. So now this screen is visible now. Hello.
Yes, sir, your screen is
Okay.
visible.
Okay. So here now you can understand like SAR signals are complex in nature. So they have the amplitude images and the phase images. Okay. So suppose this is the first image and its amplitude part looks like this. So you can say this is the amplitude image and this is the phase image. And same way I have taken another image of the next time. So this is the amplitude of this image and this is the phase of this image. So now we forget about the amplitude images in case of interferometry where we want to monitor very small scale movement. Okay, so only phase images are important, but in if you see these phase images, nothing is understandable. Means nothing we can interpret like this because these are some grainy structures. So these are not looking like an image. But if we apply some technique over these two images, let us say that is called the principle of the superposition. You might be aware about the Young's double slit experiment. So in that case, what is happening? If two images we are combining, let us say that this phase is phi 1, this phase is phi 2. So if I am calculating phi 1 minus phi 2, then this type of the structure I will get. Okay. So I cannot comment anything over this image or this image, but I can comment something over this image. And how we have generated this image? Just by differentiating these two phase images, means this one minus this one or this one minus this one. So what we are getting here? We are getting some colors. You can say some color cycles we are observing. So here you can see here it is yellow, then pink, then blue, then again yellow, pink, blue, and so on. Okay, it means a color is repeating again and again. So these are called the color cycles. In interferometry, we will call it as a fringes. So you can see for one fringe, some phase difference of 2 pi is happening. Let us say from this yellow to blue, phase difference is changing by 2 pi. Then again from yellow to blue, again 2 pi phase is changed. Then from yellow to blue, again 2 pi phase is changed. Okay, then again from yellow to blue, here the clear fringe is not there. So you can see over this small portion of the land, the phase is changing very rapidly. Means first 2 pi is completed, means phase has changed by 2 pi, means each cycle is corresponding to 2 pi. So from first yellow to first blue means from yellow to blue phase has changed by 2 pi. Then again from yellow to blue another 2 pi. Then from yellow to blue another 2 pi. So you can say, and 2 pi is equivalent to some distance, or you can say the path difference. So here you can understand like this: the width of this fringe, here it is small, here it is comparatively bigger, and here the fringe width is comparatively again bigger. It means over this portion the phase is changing over large distance. Phase is changing by 2 pi over large distance. Here the phase is changing by 2 pi over moderate distance, and here the phase is changing by 2 pi in a smaller distance. So it basically now tells us in the central part of this, the deformation or you can say displacement happening more, because in a smaller area phase has changed by 2 pi. It means more displacement is taking place in the central part, and in the middle part here you can see the moderate level of deformation is happening, or moderate level of path difference is happening. Now the path difference I will use as a displacement. Okay, so now I will frequently alternatively use sometimes path difference, sometimes displacement, or sometimes deformation also. Okay, so you can say the displacement here is less moderate and here is less, and the fringes are not very clear here. It means the phase is changing very slowly. It means the displacement over this portion is very small. So what I'm interpreting from this image, and this image is called the interferogram, because here I this graph is nothing but the phi 1 minus phi 2. So phi 1 minus phi 2 means delta phi. So delta phi is interferogram. So you can say here the path is changing very rapidly, here slowly, and here very very slowly, and here no fringe means no displacement is happening. So you can say here more deformation is taking place, but here no deformation is taking place. So what you can do, suppose from here to here you can calculate the path difference or displacement. Then again from for the next cycle, let us say from here to here you have calculated, then from here to here you have calculated, then from here to here you have calculated. So a series of displacement you can calculate. So series of displacement mean continuously, let us say from this place to this place, then this place to this place, this place to this place, this place to this place. So this way a series of displacement can be calculated using this particular concept, and this concept is called the SAR interferometry. So if you have the series of displacement, you can calculate the series of velocity also, because velocity is the derivative of the displacement. Then if you have the velocity, then you can calculate the acceleration also. So what you are having here, displacement, velocity, and the acceleration, and these three are the kinematic variables. You can apply the laws of the motion or Newton's law of motion also from this particular concept. So you see, if you are combining two images, we are able to generate this beautiful image. And now this beautiful image is linked with the displacement which is happening on the surface. And this displacement is very slow in nature, very small scale displacement. This is not like in one day I'm traveling 10 kilometers or 20 kilometers. So this is not 10 kilometer 20 kilometer path difference or the displacement. Okay, this displacement is of the order of few millimeters. Just like land subsidence, suppose the land surface is here, and this land can go down by different regions. Suppose some extra material you are extracting from underground, let us say groundwater you are extracting, or coal is extracting, or petroleum product you are extracting. Then in that case this land can go down slowly it can go down. So that is called the land subsidence. Land is subsiding, it means this displacement is there in the vertical direction, means vertically downward it is going. Okay, so this is vertical displacement is called the subsidence. It can happen because of over extraction of the groundwater or petroleum product or the mining materials like coals or ores, etc. Or there may be another region, like if extra load if you are putting from the upper side, let us say high rise buildings are there, especially in the cities. So if high rise buildings are there, then the slowly land is going downward. How much it is going? It is going few centimeters in a year. And again, suppose underground material if you are extracting, let us say water you are extracting, then because underground some aquifers are there, so over exploitation you are doing, then the land is going down. Or if you take the examples of, let us say, agricultural land, in agricultural land in summer season more water we are extracting for the irrigation purpose, so that time land is going down. Then rainy season is coming, the because of the rainfall the aquifers are again filled up. So this aquifers are expanding, the land is coming in its original position. Then after rainy season it is again slowly going down, then in summer going down, then again in rainy season going coming up. So land is going down, up, down, up, down. So if you draw this pattern of this land, so it is behaving like this sinusoidal signals going up and down. How much it is going down? Few millimeters or few centimeters in a year. So that can be done with the help of this phase difference, nothing but the phase difference of two SAR signals. Okay, another example maybe the land subsidence is across the coastal region. See, you are aware of, because of the climate change, glaciers are melting, then water is going to the ocean, and the sea level is rising by few centimeters. People are they are doing the climate related analysis, and they are concluding like this: sea level is rising every year because of change in temperature. But nobody see in the coastal region, this is the situation. Suppose this is the water level, this is the coastal land. So if water is going up, so there may be two regions: either water is increasing in the ocean, that's why it is going up, or there may be another region like water is at the same level, but land is going down. If land is going down, then also it appears like the sea level is rising. So everybody is thinking about sea level is rising, but nobody is thinking about whether the land is going down or not. So it means people are not thinking about the land subsidence, but land subsidence is much more important. Or if you are commenting like this, sea level is rising, you have to do both the analysis. You have to take analysis over the sea surface plus the land surface movement. Then collectively you can conclude whether the land is going down, water is coming up, or because of the relative motion, or land is constant, only water is going up. Then only you can see the sea level is rising. Okay, otherwise it is incomplete. So how you can check the land surface movement? With the help of the SAR interferometry. And same thing you can do for the terrain, the plate tectonic movement. Plates, earth plates are moving. Let us say our Indian plate is moving towards the Eurasian plate. So how, by which rate it is moving? Few millimeters in a year. It means this is very slow motion. You cannot observe from your eyes, but you can observe from these images if you have the satellite images, SAR images. Same way, glacier melting. So glacier, let us say, uh, initially it is here in the summer season, it has melted up to few millimeters. You cannot observe from your eyes, but you can observe from the SAR images if these types of the patterns you are observing. And the tilting of the buildings. For example, in Taj Mahal in Agra, you might be read in the newspapers some times ago, like those pillars are there in the Taj Mahal. So people are saying these pillars are moving outwards like this. Okay, but few people are saying no, this is the part of the architecture only. Means initially itself the pillar was like this only, but nobody checking whether initially they were like this, or over a period of time they have tilted outwards and now they are appearing tilted one. So this tilt, how much tilt it is? This is only few centimeters per year, or if it is few millimeters. This is not in kilometers. Means this pillar is not moved 2 kilometers or 1 meter or 2 meters. This movement is in few centimeters only. So you can observe from this interferometry. Suppose you have a series of the data set, let us say from 2000 to 2026. So over last 26 years, you can analyze whether the pillar movement is there or not. This is not actual movement in the pillar. Tilt in the pillar. Whether the top portion of the pillar is going this way or this way, if it is going, then how much it has gone in the last 25 years. So this type of the infrastructural movement you can also observe very easily. Okay, landslide movements of terrain itself is moving. You can find out in earthquake deformations. If some damage is there, that you can observe with the help of this SAR interferometry. Volcanic eruptions you can do, and you can analyze with the help of this SAR interferometry. There are so many applications of this SAR interferometry, and all these outputs are basically called the deformation. Means if anything has deformation is basically if actual shape is this one, and if any portion is tilted like this or shape has changed, it means this has deformed. So how much it has deformed, that deformation can be analyzed with the help of the SAR interferometry. Same thing you can apply over the dams. See, dams are there where the huge amount of water is coming, and dams are only the structures. So over a period of time, huge amount of water is thrusting to the dam, and the geological structure are not that much strong. Then the dam can shift slowly downwards, or the dam can tilt also. So how much tilt is there, or is there any shift, can be analyzed with the help of the interferometry. So these all are very slow motion. So you can say SAR interferometry is applicable over all those slow motions which we cannot see from our eyes. Okay, so number of examples. Bridge, you can say the dam health you can check. Bridge structures you can check the health of the bridges in the country. Okay, whether the bridge is healthy or not healthy, or even in the if some crack is there in the buildings, that you can also observe from the SAR interferometry, because the crack means the ball or the building has moved few centimeters or few millimeters. It means that this is another type of the motion of few millimeter or centimeter scale. again can be monitored very easily with the help of this R interferometry. So these types of these type of the interferograms you can observe. See here, these are the fringes only. It means here more disturbance is there, more deformation is having. Okay, here more these fringes are very close to each other. Here you can observe very close to each other. You can say here disturbance is less compared to the disturbance at these locations. The topography you can generate means how much elevation is there and all. So the concept is based on the Young's double slit experiment. You might be aware about, like, source is there, one slit is there, two holes are there. If the waves are superimposing with each other, somewhere they are superimposing in the same phase, somewhere in the opposite phase. So where they are in the same phase, the bright fringe is formed. Wherever they are in the opposite phase, dark fringe is there. So alternatively, bright dark fringes you can observe. The same things you can apply over the satellite images. For example, this one image is taken from one satellite position. So image is looking like this. Now screen is there on the surface, or our surface itself is working as a screen. Now suppose I'm combining second image. See here, if second image you are combining, then these types of the fringes you are observing. See, bright, dark, and so on. And each cycle is corresponding to phase difference of 2 pi. So accordingly, the phase difference patterns you can observe on the surface, and fringes you can observe, and you can analyze what kind of the deformation is taking place. So here you can see another example. Suppose two satellite images you are combining, you can generate the topography also. So background is the elevation model. So I'm moving quickly. So here, this is the concept mathematical formulation. This I'm just want to skip. Now, this is the ground or the infrastructure deformation has many importances, starting from the environmental conservation, infrastructure design in the cities. Suppose in the cities we are planning, drainage patterns, pipeline networks, which is underground, or the sewerage pipelines, or subsurface utility plannings, and the groundwater extraction regulations. Especially, let us, you might be aware about the Punjab state, where huge amount of water is extracted for the agriculture purpose. So now government has imposed some regulations. Everybody cannot dig the bore wells for the extraction of the groundwater. So all such examples are related to the ground surface motion, or you can say the displacement, or in interferometry we call it the path difference. So this ground deformation or the ground surface movement is very important to analyze. People are not realizing the importance. One example I have mentioned, like along the coastal region, you can comment whether the sea level is rising or not. If you are not having the surface information, then you cannot comment. Same thing, if land subsidence information you can analyze over the Punjab state, then you can recommend to the government, okay, these types of the regulations can be formed over this portion of the Punjab, and this portion of the Punjab is okay or not, or the same thing over the other states. So such types of the things or recommendations you can make. Okay, and glacier melting you can analyze, and so on. So if you see in terms of impact, so if you have the ground surface information, then it can affect the buildings or the infrastructure. So in terms, so you can say the infrastructural impacts they have, like the cracking in the buildings, tilting, sinking, breaking of the pipelines, malfunctioning of the sewerage lines. So it means if infrastructure is getting impacted, if land surface movement is happening. So you can say the land surface movement is having the infrastructural impact. If infrastructure is getting impacted, then infrastructure is associated with the money or the economy. So economic impacts are also there. And economy is associated with the society. So societal impact it has. And this has also, environmental impacts also. So another example I can give you, everybody is saying in the cities some water logging problem is there in the rainy season. Okay, so everybody is saying, okay, drainage system is not good in this city, that city. That's what the water logging problem is happening. But nobody is thinking about the land subsidence in the cities. Suppose initially the land city was planned properly, so that time slope of the city is like this. So the drainage is also along this side. So the water was going easily outside. But if you are constructing very high rise building, let us say this side, so this side land can go like this. If it is going like this, so the water water of this region cannot flow this side. So obviously the water logging problem will happen there. So nobody is thinking about whether the portion of the land is stable or not. If it is not stable, it can go down if you are putting, high-rise buildings. That it will go downwards few centimeters only, but few centimeters depth is sufficient to stop the flow of the water in the drainage system. So such kind of the problems you can handle very easily if you have, the knowledge of this R interferometry. Here I want to just show you one examples of the landslide in the Himachal Pradesh. This site is there along the National Highway 707 in the Sirmaur district. So this analysis I have done using this R interferometry, using the ascending and descending data set, and the landslide was predicted using the kinematic variables, means time series of the displacement. So here you can see I have used the two years data set from this May 2019 to July 2021. So here you can see that this is the displacement variation. So initially the displacement was not there, but after this particular date the displacement has increased very rapidly. It means the disturbance has started from this date onwards at this particular landslide location. It means if this displacement will continue for a long time, then landslide will happen. What is landslide? Landslide is the movement only. If land is moving fast, it means this is landslide. So using this particular kinematics, I have predicted the landslide also, so that in future if somewhere the landslide is situations are happening, so that can be predicted in advance, and that prediction can be done with the help of this R interferometry techniques. Another case study I have done over the Josimat area. So Josimat, you might be aware about the Josimat situation in 2023. Huge cracks have been developed in the buildings. So that time very nationwide news was there. So here you can see these types of the cracks were there in the buildings in the Josimat town. I visited the location. So here you can see the level of movement, or you can say the cracks in the buildings. So here some muddy water was also observed. So this analysis was also done using the interferometry. So here you can see the outputs. So here this is the map of the Josimat. Here you can see this one. Wherever the red patches are there, it means these are the areas affected more in terms of cracks in the Josimat area, because the land was moving downwards. Okay, so this is the displacement map, and this velocity map was there, this one, and the acceleration map was also there. So this is the acceleration map. So from series of displacement I have calculated the velocity, and from velocity I calculated the acceleration. So you see the red patches in the displacement is more, and in velocity is comparatively less, and acceleration map the red patches is comparatively lesser. Okay, so that way, but acceleration is very important. Wherever the accelerations are happening, it means that particular area is still very risky in terms of its movement. It means the buildings are not safe over that particular area, and that outputs were compared with the coast data sets, and coast data was taken from the Survey of India, where the GNSS stations they have installed across the country. So one station is there in the Josimat, so that data was compared with the interferometry data sets, and they were matching perfectly. So you can see this type of the motion. And this study I have done over the Ludhiana city for the land subsidence. So here you can see the southern portion of the Ludhiana city was also observed as a subsidence. Okay, so subsidence is happening in the Ludhiana city also, only in the southern portion, not in the northern portion, because that side river is there. So some charging of the aquifer system is there. So northern portion is not subsiding. So now here you can see some another example. Here is the monitoring of the tunnel activities. So suppose some tunneling activities are going on. So the upper surface of the land can slowly go downwards. So from interferometry you can observe, see this particular patch, yellow patch is itself is showing there here that some deformation is happening, or you can say land is slowly going downwards. So easily you can identify over this particular area the tunnel is forming inside. Okay, so tunneling analysis can be done. Here you can see the building monitoring, urban monitoring. Here, wherever the red patches you are observing, it means the land is going downwards and the health of the buildings is not good. And this is the output of the interferometry only. Here you can see the mining or the tailing dams, means the extra material they are putting over a particular locations, and that is called the tailing dams. So how the size of the tailing dams is increasing or decreasing, so that can be analyzed with the help of the interferometry. So wherever you are able to see these red patches, it means that particular area is changing either in up direction or in the downward direction. This is another examples of the tailing storage facilities over the mining areas. And this is another construction work. Suppose a particular colony is being developed by the builders or someone else, and if they are not doing the construction properly, they are not checking the foundation or the stability of the land, but you can check with the help of the interferometry. So wherever you are observing the red area, it means those buildings are moving, either in the downward direction or in the upward direction. So that kind of movement you can observe over the cities or the colonies also. So the construction work you can basically monitor. This is another early warning systems. If landslide is happening, so how it is happening and how you can predict. I have shown you another case study over Josie, their Sirmaur district. So that early warning things or prediction part can be done over the landslides. Here you can see the long-term maintenance activity. Suppose some maintenance is required in the cities. Somewhere pipeline has dropped, somewhere drainage is broken. So if you are doing an interferometry analysis, so wherever these red patches you are observing, it means something is disturbed or some deformation has happened over those locations, and accordingly you can basically go and check the health of the infrastructure or utilities. And this is another example of the transport corridor, highways or the railway structures. So railway structures are also deforming. If railway track is old, they can deform. And how much they are deforming? They are not deforming in meters or 2 meters, something like that. They are deforming only in millimeters or centimeters. So that health you can check using interferometry. But from eyes you cannot observe. And you can check the health of the airports, ports, dams, or the bridges. You can see this is the bridge structures. So this portion of the bridge is basically deformed. So how much it is deformed? So that kind of the time series can be derived from the SAR interferometer. This is another example of the land subsidence in the mining areas. And this is open pit underground mining operations. Suppose this particular area is giving red patches, means this is highly affected. If it is underground mining activities, if you draw one patch from here to here, so the pattern you can observe here means over this particular area huge amount of mining activities are happening, and over this area less, means over this area less mining activities, here huge, here moderate. So the level of mining activities you can monitor with the help of the interferometry. This is another example of the enhanced oil recovery. Suppose this is the interferometric map. If you draw one segment from here to here, then you can observe like this type of the patterns. See here it is yellow. It means less amount of oil is extracted. Here it is blue. No oil is extracted from here. That is going upward direction. And it is red. It means again huge amount of oil is extracted from this portion. So these types of the activities can be easily monitored without disturbing the underground situation of the land. So, or you can say this situation you can monitor from the upper side or from the space itself. Okay. So this is some moisture calculation. Soil moisture can also be calculated. So these are difficult equations. It will take some time, but I have calculated the soil moisture using the SAR polarimetry data set over the Roorkee region. So soil moisture means where is dry soil, where is wet soil, where the soil water content is more, means where is the drought situation, where is sufficient soil for the crop health. So such kind of the activities can also be done with the help of the SAR data sets. So thank you very much. I have exceeded the time actually in between some internet connectivity issues were there. So now we can interact. If you have certain questions, I can take. Yes.
Shantanu, Please ask a question.
Sir, my first question is that, sir, from your first slide, I noticed some names like 300 Z hertz, then E hertz. So, sir, can you tell me that what are that letters representing
Those are
before
basically
the hertz?
gigahertz. That is frequency like hertz, megahertz, gigahertz. So those are the giga frequency in gigahertz. Here you can see this slide, correct? So you can say the.
Yes, sir, in
Are
the
you able to
first
see the
slide.
screen? Are you able
Yes,
to
sir,
see
yes,
the
sir, yes,
screen?
sir.
Yeah. So current
Yes, sir, yes.
frequency changing from 27 gigahertz to 40 gigahertz. Okay, so this is a unit of frequency, nothing else.
No, no, sir, that red one, marked in the red.
In the red one, this one. See, this is
Yes,
the
sir, that
basically this is
Z
range.
hertz,
See,
E
this
hertz,
is
then E.
range means suppose here I have highlighted the visual portion. So but this is the boundary of these are the boundaries of the visual portion. So visual portion is ranging from 400 nanometer to 700 180 nanometers. So 400 nanometer is a wavelength, correct? And what is the frequency?
Okay.
Frequency will come 750 terahertz, and if you put in terms of energy, then it comes 3.3 electron volt, and if you are writing it in terms of wave number, then it will come 25,000 per centimeters, or you can say wave number of the 25,000. So basic, this I have mentioned because different people uses different units. Somebody is very easily use the wavelength units, somebody use the frequency unit, somebody energy unit, somebody wave numbers, and so on. So all possibilities I have written here. So but in case of remote sensing, only frequency, or generally we are taking the wavelength. Okay.
Okay, sir. Next, we have a question from Kaushik.
What is the question?
Kaushik, please ask your question.
Sir, good evening, sir.
Good evening.
Sir, I have regarding doubt about maintaining career on remote sensing field. So, what tools shall I need to learn in order to become a perfect remote sensing engineer?
See, remote sensing is not so easy. Okay. There are, as I mentioned, there are different types of the remote sensing. Like a lot of work you can do in optical remote sensing, lot of work you can do infrared, lot of work in thermal, lot of work in the microwave remote sensing. So you cannot be expert of all the remote sensing fields. Okay. So you can pick any one of them, and if you want to take some extra advantage, then you can go with the microwave remote sensing, because as I mentioned, these data sets are useful in disaster situations also. So the scope of this technology is wider compared to the other remote sensing techniques. So you can handle these types of the situation, but whatever I have told, and you can handle disaster situations, you can handle agriculture problems. In agriculture also, see, crop is initially size is small, then over a period of time size of the crop is also increasing. So the moment it is increasing, the response in the SAR images is changing. So how much it is changing, that the growth of the crop you can monitor from the SAR images. And if some disease is there, then the response in SAR images over the diseased patch of the crops is different from the healthy crops. So if any disease is happening, so you can say the crop health monitoring you can do. If you want to monitor, let us say, total production in the agricultural field in the entire country or in a particular state or a particular district, that thing you can monitor. So the chances are more in case of radar remote sensing.
Sir, I mean about is this remote sensing come under physical design field or I mean digital signal processing field, or
Yeah,
it I mean
so
coding related, or
this
it is
depends, this
physical
depends
design?
on your interest or specialization. If you want to work with the signals, then you can work with the signals, because there are so many terms at the level of signal processing, like focusing, azimuth focusing, range focusing, okay, and the filtering, phase unwrapping. So many terms are there at the level of signal. Okay, so huge number of things you can do with the signal processing part. And if you want to develop the sensor, then you can work with the sensor development. Be that sensor development for radars is different from the optical sensor development. So from the sensor design, in sensor design you can develop your career. In signal processing you can develop your career. In remote sensing part you can develop your processing part, and in the application part you can also develop. So this is up to you. You cannot handle all of them alone, okay, because each field itself is a very big field. So as per your specialization, you can pick any of the field from the sensor development to the application.
I mean, sir, in hardware, how many types of roles we can see from remote sensing field
In
in
hardware,
hardware domain?
in hardware domain, see, optical system you can develop, microwave systems you can develop. Hardware means only sensor development, okay, and satellite is different. Satellite is a platform where we can put the sensors. But if we are developing the hardware of the microwave sensors or radar sensors, so you can check basically like X band radar, C band radar, L band, P band, and so on, because the characteristics of all radars with different wavelengths is different. So this is a huge field actually. So a lot of chances are there. And nowadays people are not able to develop these hard sensors. Suppose in developed countries people are having the airborne radars and they are doing the field surveys. But in India we don't have. Now the Pixel, one company is there, Pixel, they have developed some radars and now they are acquiring the data sets. Okay.
Okay, sir. Thank you, sir.
Yeah.
So next we have a question from Y. Danit Uzwal.
Good evening, sir.
Good evening.
Sir, so my doubt is the satellites which are deployed as a part of the SR, are they going to be scanning a particular target or are they going to scan a huge area?
They are scanning huge area. That example I have shown, no, that is basically uh, uh, in terms of improving the resolution. But see, the sensor is looking like this. The way we are looking, the same way the sensor is looking. Suppose we are looking, it means we are covering this much area. So that at the moment the distance is increasing, just like a torch. If you are putting a torch over here, the coverage is small. If torch is at a distance, then the coverage will increase. If further we are increasing the distance between the torch and this screen, then the coverage will be increasing. Okay. So same way the sensor is there in the space. So the coverage over the surface is very large. But that explanation I had did by just considering a particular target. Means for a particular target, in how many ways the sensor will look the same target. This is not only go for that particular target. This is for all the targets. Means suppose in one scan, this much area is scanned from one satellite position. From another satellite position, 90% area is repeated, or 95% area is repeated. Then another scan, another again 95% area is repeated. It means a particular target is visible from the sensor location in multiple scans. That's why I mentioned the same target can be seen from multiple satellite positions, and that way the antenna length is increased. Okay, so this is not a single
Okay.
target. This is a bigger area, generally in the form of the rectangle.
And sir, the satellites will travel around the Earth with very fast, no, sir.
Yes.
So are they going to remember a particular coordinate of the image, and are they going to match with the same image after the completing the rotation?
See, satellite is moving very fast, and the area which they are covering over the Earth surface, that is also very large. That is, let us in one snap they are taking 400 kilometer by 250 kilometer. So 400 kilometer is very large distance. This is not a small area like in the picture of a mobile phone, something like that. This is not like that. 400 kilometer by 250 kilometer, one scan area is there. Okay, so just visualize
Okay.
that particular dimension, not the smaller dimension of the one scan.
Okay, sir.
Hmm.
Sir, and are we like how can we access these images, sir? Like in government
Images,
websites, are they provided?
images you can access from different portals. For example, every space agency is having their own portals. Like ISRO, we have the Bhunidhi. So you can search on the internet Bhunidhi of ISRO. You can download data from there. And if you want the space science data, like the data of the Mars or the Moon, then ISS site is there of ISRO. ISRO Space Science Data Center. And the full form is ISRO Space Science Data Center. So from that site, you can take the data of the Mars or the Moon or any other foreign satellite data sets are there. Those data sets are also available. Okay, so this is for the ISRO. For NASA, Alaska Satellite Facility portal is there. So from there you can download. From the European Space Agency, they have the Copernicus site. So from Copernicus site you can download. Okay.
Okay, sir. Thank you, sir.
All right, so we have one more question from Vidisha.
Yeah.
Vidisha, ma'am, please ask the question.
Hello, sir. I
Yeah.
just want to ask that using this satellite technique, remote sensing, can we use it to detect the crime rate or something like live event of crime happening or not somewhere in
No.
world?
No. Answer is no. Crime means these are the momentarily events. Crimes happens, in 5 minutes, 10 minutes, or 20 minutes, something like that. But satellite is completing its one revolution, let us say in 4 hour 24 hours or 12 hours or sometimes 24 hours. And
So,
so suppose the crime wherever the crime is happening, that time satellite is not there in the space, means that time the satellite is at the another portion of the globe. It means that crime cannot be captured. And crime means the size of the individuals, which is means pixel size should be very very small. Very high resolution data sets are required. Okay, so those
oh,
things are not there. And from the satellite images you cannot identify the individuals who are doing the crime.
and sir,
Okay,
one
so
question.
hmm.
What is the like our mobile is also have the energy like microwave has the energy of wave or length. But our micro like the it's not equal to the but there is a latest trend over there that we are using the earplugs the which is Bluetooth connected and these are wave are not good for our brain. Is this also not good for our health? I ask these general questions like it's they are using the technology like
See,
wavelength are not good
I
for
could
my
not understand your
brain.
full question because your voice was missed. But what I understood is you are asking about the radiation which is being used in the remote
Yes, sir.
sensing devices, correct?
Yes, sir. Yes, sir.
Yeah. So see, in microwave radiation, the radiation is not good for health. Okay.
Okay.
If that radiation is put it on your body beyond a certain threshold. Okay. But in this remote sensing signals, the amount of energy is very very less. And another important thing is when we are doing from the radars, these are the waves actually, not the direct radiation which you are receiving from the sun, like optical energy you are receiving, and that is directly going on your body. But micro waves, these are not rays. See, there is a difference between cosmic rays, x rays. Here it is waves, radio waves, microwaves. It means these are having the wave nature. So wave nature means the wave kind of, or you can say kind of disturbance is happening in the medium. So the disturbance is incidenting on you if you are there. Okay, and this
Okay.
disturbance may be dangerous if wavelength is longer. Wavelength is longer means that can penetrate inside the skins also, or some skin disease may develop. Okay, so you can say longer wavelengths are harmful, radio waves are harmful, and P band is harmful. But L1 is also harmful, but little less. Okay, as C or X band, they are not that much harmful. So because of that, nobody has developed P band SAR. But recently, the European Space Agency had developed the P band SAR for the biomass calculation only. But they are acquiring the data set very, very carefully. They are not using those signals which can affect the health of the human beings. Okay. So yes, of course, longer wavelengths are dangerous for the human beings, but the smaller wavelengths are not. Yeah. Any
So
other
I
question?
have one. Yes, sir, from somebody connected from device named such as 91945. Please ask the question. And I request all the participants kindly join the meet with your own name.
Okay. Please finish quickly because now it is already 9:30, so I have to go outside for some work. Yeah, please ask quickly.
Okay, sir. Good evening, sir.
Good.
Sir, I wanted to ask, once when we look at the satellite image of some place, like once I was looking at the satellite image of my village field, crop field. So once I viewed the image of 2008, there was the same image of my field. And when I looked at the image from 2016, or like after 3 or 4 years, then the same field was showing up different latitudes. Like my field was there already in 2006, the field was at the same place, and after 2008 at the same place,
No,
but it
I'm
was
not.
showing
See,
different
satellite
latitudes.
data sets are available. So the satellite data available from 1970s onwards. So wherever you want to observe, you can use that one. But
No, sir, I'm just giving you just an example. The year changed, but the field isn't. Okay, the field was at the very same place. I mean, I have seen it in the very recent, like in 2016, I have seen the field is same, but when we change the year of observation, like in gap of 2 or 3 years, it changes a
your
slight
voice is
difference
cutting.
in
No,
the
no, I'm
latitude.
not getting exact message from you.
Okay. Sir, are you comfortable in Hindi? Maybe it would be clear.
Okay.
ओके सर, मैंने मेरे खेत का सैटेलाइट इमेज देखा था 2022 के आसपास में देखा था। तो सर खेत मेरी ही जगह पे है, बट द प्रॉब्लम इज कि उसका लैटिट्यूड 2 साल बाद किसी और प्लेस पे दिखाने लगता है, सेम प्लेस का लैटिट्यूड चेंज हो जाता है, स्लाइट डिफरेंस आ जाता है इमेज में। ऐसा क्यों होता है?
इसमें क्या ना, दिस इज द प्रॉब्लम ऑफ द कोऑर्डिनेट सिस्टम। एक्चुअली आप जब कोऑर्डिनेट सिस्टम पढ़ेंगे तो बहुत टाइप के कोऑर्डिनेट सिस्टम होते हैं। उसमें जियोइड होता है, फिर कोऑर्डिनेट सिस्टम, फिर प्रोजेक्शन सिस्टम। तो क्या है कि कई तरीके के हैं और कोई भी परफेक्ट है नहीं। तो आपने कहीं ऐसा देख लिया होगा कि पहला वाला डेटा सेट देखा वो कोऑर्डिनेट सिस्टम ए में है और दूसरा देख लिया बी में है, तो थोड़ा शिफ्ट दिखेगा फिर आपको।
सर आई वाज यूजिंग द सेम, लाइक आई वाज लुकिंग एट इट विद
तो
द गूगल अर्थ मैप।
सैटेलाइट जो भी एक्वायर किया जिसने डेटा, तो उसमें करेक्शन जो करने पड़ते हैं ना प्रॉपर जियो रेफरेंसिंग के, तो वो जियो रेफरेंसिंग प्रोसेस कंप्लीट नहीं हुआ होगा। अगर कम ठीक हुआ है तो फिर वो शिफ्टिंग नहीं मिलेगी आपको।
अच्छा, मींस अपडेट होता है बार बार, इसलिए वो चेंज हो जाता है लैटिट्यूड।
नहीं, कहाँ पे आप चेक कर रहे हो ये?
सर गूगल अर्थ पे था।
गूगल अर्थ पे कहीं कहीं पे थोड़ा शिफ्टिंग है, क्योंकि देखिए पूरा ग्लोब का कोई एक इमेज नहीं है। जब सैटेलाइट एक्वायर करता है ना तो एक स्ट्रिप में करता है, तो एक स्ट्रिप ये हो गई, दूसरी स्ट्रिप हो गई, तीसरी स्ट्रिप हो गई। जो स्ट्रिप को जब मर्ज करते हैं तो कहीं कहीं पे मर्जिंग की तरफ से प्रॉब्लम आती है। तो कहीं कहीं पे आप जब जूम करते होगे ना तो कहीं कहीं ज्यादा ब्राइट दिख रहा है, कहीं कहीं पे डार्क दिख रहा है। तो वो यही है कि जहां पर ब्राइट दिख रहा है तो हो सकता है कि वो वाला सीन अपडेट हो गया है और उसके एडजेसेंट वाला अपडेट हुआ ही नहीं है। हो सकता है कि वो पहले की इमेज है और उस समय क्लाइमेटिक कंडीशंस कैसी रही होंगी जिसकी वजह से थोड़ा सा डार्क दिख रहा है।
सर इशू ये होता है कि वो लैटिट्यूड ही बदल जाता है।
नहीं नहीं, ऐसा नहीं होगा, ऐसा नहीं होगा, फिर से चेक करिए। ऐसा होता नहीं है, बट एक हो सकता है कि दो सीन के कोई बाउंड्री पे ही आपका खेत पड़ रहा हो तो उसकी वजह से आपको थोड़ा ऐसा ऑब्जर्व हो रहा हो। तो ऐसा हो
maybe
सकता है,
वैसा लिखे
अदरवाइज होता
है।
नहीं। हाँ,
Okay.
ठीक है।
All right, sir. Now we can end the session. So, do you have
Okay.
anything to say, or shall I end the session now?
Yeah, it's fine. So tomorrow we will have some practical demonstration of this same interferometry data sets. Okay, there I will tell what type of the tools are there and from where you can download the data set, how you can install the different softwares, and how you can process it. Okay, so that I will demonstrate in this laptop only, and if you want you can carry your laptop also, and same time you can also practice. Okay, though I will share the tutorial also, so all the steps will be written in the tutorial. Okay, so thank you so much.
Thank you, sir, for such an insightful session. Thank you, all the participants. Now you all can leave the meeting.